All right. So without further ado, let's get started. So hello everyone for week 2. I think we're moving pretty fast. You're already 1/5 into the course. And today we're going to talk about Boolean algebra. Essentially pick up from where we left off from last Thursday, and then continue our discussion about this new algebraic system and see how we can manipulate the expressions to implement a cheaper and more compact combinational circuit. So here's today's agenda. It's all about Boolean algebra. We're going to see the definition of Boolean algebra and visualize some of these axioms and theorems. And then we're going to see how to use truth table to establish equality or inequality, just like what we did before last Thursday. And we're going to see some interesting properties relating to Boolean algebra. And finally, I'm going to show you some algebraic simplifications proofs. Yes? We're going to get to there in just one slide. All right? So Boolean expression and circuit, they're just very related. You can convert a Boolean expression in terms of variables into a circuit by just hierarchically decompose the Boolean expression. So for example, the first Boolean expression, ab prime plus c, at the top level, it is an OR of two components, right? OR between ab prime and c. So we can put down ab prime on one side of an OR gate, c on the other side, to build that Boolean expression. But ab prime is still a function, so you need to further decompose it into individual variables. So what we do, well, it's an AND function between a and b prime. So we put down an AND gate, connect a to one side, b prime to the other side, and b prime is the inverted b. So adding an inverted to the b side, this gives you the circuit implementation of a Boolean expression. And similarly, for the more complicated expressions, we can hierarchically decompose it by first realizing at the top level, it is the OR of two sub-expressions. And one of them is BE, so I put BE at the bottom with an AND gate. On the top level, it is the complement of another expression. So I just keep breaking it down little by little until I reach some individual variables. At that point, I'll connect those variables to the input of the gates or input of the circuits to build my overall expression. Where's my definition of axioms and theorems? I'll get to there in 15 slides. So axiom is something that is true by definition. Theorem is something that can be proven based on the axioms. All right. 15 slides, a little bit more than one slide. All right. Again, the definition of Boolean algebra. Boolean algebra is defined, well, actually it's two-value Boolean algebra, the one that we use for switching circuits, technically speaking. That is defined with a quintuple of 5 things. We need to define the set of elements that we can use. Those are zeros and ones, right? And all of the circuit components, AND gate, XOR gate, OR gate, they're dealing with zeros and ones. And that's how we define the input space to be 0 and 1. And there are two defining operations, AND operation or operation. These are like two very fundamental operations. And for each operation, there's an identity element that allows you to apply the operation through this identity element to get back to the same input variable. And with that, that's the definition of Boolean algebra. And those are axioms, which means they cannot be proven. Those are just defined to be true. Right? And for example, if you take out one of these axioms, you cannot really prove it from the other axioms. Whereas for the theorems, those can be proven based on this set of axioms. Right? And let's take a look at a few of these axioms. I think an easy way to visually understand those axioms is by putting these gates in a two-dimensional truth table, right? Like a two-dimensional input-output table showing the output behavior. Right? AND gate is 1 only when both inputs are 1. OR gate is 1 when any of the input is 1. Right? And again, the identity element is the one that is associated with each operation. For OR gate, or anything with 0 gives you back that input variable. And anything with a 1 gives you back that input variable. So identity is kind of easy to see. Commutativity is saying that we flip the order of the two operands, x operation y and y operation x. They should give you the same result, which means the table should be symmetric across the diagonal. Because we put one variable on top, one variable on the left. So if you go from here to here, you should really get the same value. Right? Between here and here, they should be the same. So visually speaking, the table is symmetric across the diagonal. Right? So let me just point out the two elements that I'm looking at. Right, 0 output 0 and 1, 1 and 0, they have the same output result. 0 or 1, 1 or 0, also the same. Right, so being symmetric across the diagonal means that these two operations do satisfy commutativity. Identity. Well, each gate has an identity element. For AND gate, that is element number 1, or element 1. For OR gate, it is element 0. Identity element, when you take that through the AND gate with any other input variable, with 0 should give you a 0, with 1 should give you a 1. So you observe one row and one column in this 2D truth table. That is the same as the headers. So this is my header, 0 and 1. And when you look at that column, essentially when you fix the other input to be a 1, you should get back the same input variable. Right? Similarly, you look at the column headers, 0 and 1. And then this row should also give you back 0 and 1. And similarly, 0, 1 gives you 0, 1. 0, 1 gives you 0, 1. So the column and row indexed by the value of 1, that is the identity element for AND gate, by 0. So the identity element for OR gate is a 0. All right. Complement is a bit complicated. You see, if you look at the complement axioms, right, for the OR definition, the result should give you a 1. 1 is really the identity element of the AND gate. So complement theorem is really saying a variable together with its complement when going through operation 1 will give you the identity element of the other operation. So there's a bit of connection between these two gates in the definition of Boolean algebra. Right, for AND gate, A and A prime will give you the identity element of the other gate. Or if you assign some more concrete number, 0 and 1 gives you 0, 1 and 0 gives you a 0. Right? It's kind of easier to prove if you just plug in the two values, 0 and 1, into that formula. Similarly, for the OR gate, identity element, right, 0 and 1 will give you the identity element of the opposite operation. So right now we're operating at a little bit of the intersection between formality and the more concrete two-valued Boolean algebra. Right? Formally speaking, this is how they interact. But numerically speaking, in terms of zeros and ones, you can easily plug in those values into the expression to verify the correctness of the algebra. Right. Again, so far we're still recapping last Thursday, right? The definition of Boolean algebra. Distributivity is kind of hard to visualize because it involves 3 variables. And this table only shows you 2 variables. Right. So what do we do with it? Well, we bring back our good old friend truth table. Remember, this is what we did for that car. The truth table that defines input-output behavior by enumerating all the input combinations and then specifying whether each output is 0 and 1 under each of those input pattern conditions. We can do that for a Boolean expression, actually for multiple Boolean expressions, and then compare them side by side to see if they are equivalent. In this case, A plus BC, well, you could directly write out this column for A plus BC by just plugging in each of these 3 values. But what I find convenient is you, again, break it down into some small expressions so that you can more quickly fill out those sub-expressions before representing your final expression. So A plus BC is A, well, just the input variable. I already have a column for that. Right? BC, I can write it as a new column. And it will be 1 when BC are both 1s. Right? I can quickly fill out that column for BC by just looking for this known condition to produce a 1 and then fill in the zeros for the rest. Right? This essentially prevents you from really running those numbers through the operation, but rather just more conceptually understand BC as the intersection of 2 columns. Right? And then A plus BC will be 1 whenever A is 1. So those 1s will be propagated to the output. Whenever A is 1, output will be 1 right away. Or when BC equals 1, and that will also propagate it to the output. Right. The other side of the expression on the right-hand side is a little bit more complicated. Right? There are 2 sub-expressions, A plus B, A plus C. A plus B would be 1 whenever A is 1 or B is 1. So those are all the 1s I got. Right? A quicker way to fill out the truth table is by just operating with basic gates, so that you can think of every operation as the union or intersections of two columns. And then A plus C will be 1 when C equals 1, and or A equals 1. So those are represented over here. And finally, the end of those two columns, the end between A plus B and A plus C would be, well, when both of them are 1s, the output will be 1. So those are the 6 rows, right? When both of these are 1s. And with this, now if you compare the A plus BC column and the A plus B and A plus C column, they're exactly the same. And that allows you to conclude that the left-hand side and right-hand side are identical. Yeah. Any questions? Max, you look visually confused.
Just give me a second. Just keep going. I got it.
Okay. All right, you sure?
Yeah.
All right. So now I have an exercise for you. Right? I showed you that and or, they do constitute a Boolean algebra. And that is the definition of the normal two-value Boolean algebra that we use in this class when dealing with circuits. And XOR, if I give you these two operations, do you think they satisfy those axioms? Right? Like, do you think I can define those axioms for these two operations to be true? Right? I'll give you some time. I'll give you a minute to think about some of these axioms and try to visually analyze them from these 2D truth table. And then we'll work together to really make the proof. Right? Why that this is a Boolean algebra? If you think this is a Boolean algebra, it has to satisfy all of those axioms. If it's not a Boolean algebra, you just have to find a single point of failure. Right? Again, try to think of it visually if possible, particularly for those simpler axioms and later theorems, right, before working with the truth table. All right, time is up. Could somebody tell me whether these two gates satisfy commutativity? Yes, Max.
I thought I was going to say n XOR wouldn't satisfy distributive property. That's how I was going to say.
Yeah, let's go through them one by one. Right? We'll get to a distributivity in a second. So what about commutativity?
So it doesn't matter if you flip the x or y for n. If you flip for n, if you flip the x and y, it will still stay the same. That's why it's 1 though. Is what output will be 1. Therefore.
Yes, we're looking for those two diagonal cells, right, at the top right and bottom left corner. And they do have the same value within each function. So these two operators do satisfy commutativity. Right. What about identity? Could you find the identity element for each of the two operators? Again, you see, commutativity and identity, they work just within each individual function, right? So you can verify that independently for the two operators. What about identity? Yeah. Anyone can tell me if you can find an identity element for these two operations? Yes, Eric. Yeah, 0 XOR A is equal to A, is equal to A. And that is true, right? We can find this column of 0, 1 and this row of 0, 1 when one of the input variables is fixed at 0. So 0 XOR anything gives you back that original variable, right? Or you can expand this to be saying 0 XOR 0 is 0, 0 XOR 1 equals 1. Therefore, 0 XOR any variable gives you back that original variable. And AND gate always has the same identity element as before, of course. And that identity element is 1. Right? So I can just say, well, for AND gate, the identity element equals 1. For XOR, the identity element equals 0. So identity checks. Right. Complements. What about complements? Right. Well, I have two variables, and they must be complement to each other. I really have no other choices. So 0 and 1, suppose they are complement variables. On the AND side, they AND to the identity element of the other operation. On the XOR side, again, the XOR to the identity element of the other operation. So it does satisfy complements as well. All right. So Max, now I'm getting back to you. You said that it does not satisfy distributivity. How did you figure that out?
Because for n, it wouldn't make sense, right? Because for distributivity, it A times B plus C must equal to A times C. But
yes.
For n, B plus C could be 0.
1 second, give me 1 second. Right? So we're saying, okay, if we replace the OR with XOR, is this still true? That's what we're trying to verify. Right? So tell me again what you just said.
So for B plus C, inside the parentheses, it could be 0. Therefore, for n, that expression, it will be 0. But on the right-hand side, like A times C could be 0, and A times C could be 1. Therefore, it wouldn't satisfy. Is that right?
I think I caught it right. So you're saying, well, let's say if I have this value, right, 1 XOR 1. Through the XOR function, they'll give you a 0. Right? So that will make the left-hand side 0. Right? I'm plugging in B equals 1, C equals 1 into that XOR function on the left-hand side. Gives you a 0. 0 and anything is a 0. So left-hand side is 0. But you can probably find some value on the right-hand side to give you a 1 at the output. Right? So let's say if you do 1.1 XOR 0.1, which gives you 0 XOR 1, which gives you a 1. So the right-hand side equals 1. That's not quite, right? I'm assigning different values to the variable a. So this example doesn't quite work. Did I catch you right,
Yeah,
for example? Or did you give me an opposite example?
Oh, I thought just like you can make the left-hand side 0, make the right-hand side 1.
Okay.
There will be a scenario.
Yeah, give me an input variable to make the left-hand side 0.
Left-hand side could, B and C could be
A equals 0.
Yeah.
0 and 1. Indeed, 0.1 gives you 0, right, on the left-hand side. So if I plug in that value to the right-hand side, right, 0 and 0, XOR 0 and 1. Right, again, parentheses essentially happens over there. And this gives you 0, XOR 0, which is also 0. A equals 1, B equals 1. Yeah, let's try this. Okay, so on the left-hand side, I have 1.1. Right? 0 XOR 1 is a 1. 1.1 is a 1. So now I'm making my left-hand side a 1. What about right-hand side? Well, I just need to plug in those values into the expression. 1.0 XOR 1.1, which is 0 XOR 1, which gives you a 1. Right? It still doesn't quite work.
Let's try like the first equation.
You see, we're trying many things, and it just doesn't work. Right? You found another one? Give me the number here.
Let's do a plus b times c equals a plus b times c. Let's have a, wait.
1, 1, 0. Left.
Like the first equation.
The first one.
Yeah.
We're going to go with the first one.
Yeah.
Right. 1, 1, 0. Right, for ABC. Is it a random number you threw at me, or?
So it doesn't matter, right? It doesn't matter if I said b, c to 1, 0, like the output.
Yeah. Let's say 1, 1, 0, right?
Yeah.
So left-hand side would be 1 XOR 0, which is 1. Right, right-hand side would be 1 XOR, this is 1, 1, this is 1, 0. Right-hand side would be 0 dot 1, which is 0. Very nice. We finally find one. Yeah, we find a counterexample showing that distributivity does not hold. Right? Left-hand side, right-hand side are not equal. And therefore, it violates distributivity. So these two gates do not constitute a Boolean algebra. Very nice proof. But it takes us a lot of efforts. It would take you a lot of efforts. Unless you put that in a truth table. And then think of these operations that happening column by column so that you can quickly fill out essentially all the conditions and do a comparison. Right? You can, of course, think about them more conceptually in terms of, well, under what conditions this is like more likely to be a 0, the other side is more likely to be a 1. That's perfectly fine. But it will take you a lot of time. Right? And we need some tools, and these tools are just things that people have already developed to help you to simplify the task. And we better make use of them. So let's say for this, I'm trying to make this proof. Essentially, both of them will fail. So I'm approaching one of them through the truth table. Right. I already put down the column for BC. Right. BC is 1 when they are both 1, 1. 1, 1, 1, 1 gives you a 1 in the BC column. And then A XOR BC, well, if they differ, if A and BC are different, output will be a 1. Right. So this would be a 0, 0, 0, 0, 0, 1, 1, 1, 1, 0. You see what I'm doing? I'm comparing this column with this column. And when they differ, the output of A XOR BC will be a 1. Right. Similarly, for that A XOR B and A XOR C, I already put down the XOR between AB and the XOR between AC as two separate columns. And whenever both of them are 1s, right, the final expression on the right-hand side will be a 1. 0, 0, 0, 1, 1, 0, 0, 0. And now you can not only just find one counterexample, you can find all the counterexamples showing that the left-hand side and right-hand side are not the same. And those would be these two rows, right? For those two input combinations or input conditions, left-hand side produces a 1, right-hand side produces a 0. So this tells you all the counterexamples. I would say this is a little bit better than just staring at that expression and then try to construct counterexamples. But feel free to use either method. Right? It's really up to you. Yeah. Any questions? Right? And again, to sum it up, because these two gates violate distributivity, right? Like they just don't match up with each other. This is not a valid Boolean algebra. You cannot build a Boolean algebra using these two gates, right? Which means you cannot manipulate a Boolean expression with AND and XOR and then apply those XOR-based theorems. Yeah, any questions? Yes, Eric.
So does it just not work for this?
But the other one, I think both of them will fail. Yeah, the bottom one will also fail. But it takes some time to just find the counterexample, right? But feel free to try out the truth table. And well, that's actually a good question. Is the bottom one correct? Now that I think about it, the bottom one is actually probably correct. So this part part of distributivity works, but as long as there's only a single like failure for any of the theorem, or even half of the axioms, then it's not a Boolean algebra. The bottom one is actually correct. I'm pretty sure it's correct. Right, so this one is actually true. Right, the statement, the equation is true, which is an interesting observation. But would I know that beforehand? The answer is no. Right? I have to try the truth table, or later on apply Boolean algebra or some of the more powerful reasoning tools to make that proof. All right. So now we're coming back to Mitchell's question earlier, the difference between axioms and theorems. Axiom is a mathematical statement which is assumed to be true even without proof. So essentially, the way it works is we first define those axioms based on the two operators, and or, and they're assumed to be true. Well, in some sense, we build AND gate and OR gate because those axioms are true. Right? To satisfy those axioms, you can only use AND and OR gates. And a theorem is a mathematical statement whose truth has been logically established and has been proven, which means these are some additional statements that get proven based on the axioms. Right? Once you define the axioms, you can prove more theorems, and you can use that wider set of theorems for your simplification purpose. And another thing is a conjuncture. A conjuncture is a statement that one believes to be true but has not been proven yet. Right? I just assume to be true, and that's probably something I want to prove. It's my conjuncture for now. And there's some other names, like the less important theorems are called proposition, lemma, and corollary. The slight difference is that lemma is something that is like an intermediate step in your proof, and you're trying to use it to prove more theorems. And corollary is like the concluding theorem. But again, these are like purple slides, so don't worry about it. But for Boolean algebra, we need more theorems. The axioms are good, right? Good as a definition, but they're sometimes not quite powerful enough to help you simplify a Boolean expression. And with more theorem, your job gets much easier when it comes to simplifying a Boolean expression. We have idempotency. An variable operator, the same variable, gives you the same variable. Right? 0 plus 0 equals 0, 1 plus 1 equals 1. Very easy to prove with the two-valued Boolean algebra. Absorption, a plus ab equals a. Right? That's a little bit harder to prove, but we'll see that in 1 second. Identity absorption, a plus 1 equals 1, right? 1 plus 1 equals 1, 0 plus 1 equals 1. Essentially, as long as you send in an input of 1 to the OR gate, output is 1. Associativity, well, you can like change around the position of the parentheses, and the expression remains the same. Involution is saying that if you double complement any variable, 0 complement, you get back to 0. Right? 1 complement, you get back to 1. And I just told you that these are theorems, which means they can be proven based on the axioms. Right? So let's see some of those proofs. Right? Idempotency. This is actually a question I want you to, I want to ask you. How do you think we can prove this very simple theorem based on the axioms? Any ideas? How do I approach the proof? Just plug in. Well, plug in works, right? Essentially, you build a truth table for the left-hand side, right-hand side. You prove that they're the same. That's fine. But one thing you have to pay attention to is that these Boolean axioms or theorems, these are theorems that are true for any Boolean algebra, not just two-valued Boolean algebra. And you can build a Boolean algebra with a lot more variables. You can build an 8-variable Boolean algebra, a 1024-variable Boolean algebra. And by that point, truth table is no longer feasible. So I want you to approach them algebraically by using the Boolean algebra so that whatever proof you get remains valid for any number of variables. Right? A more powerful way of approaching the proof based on the definition of the algebra, the axioms. I think, Eric, you were raising your hands. Yeah. How would you prove this? Yeah, the first distributivity. You think of this as a BC? Yeah. Okay, so this one is a plus a times 1 by identity. Right? 1 dot a gives you a. Give me 1 second. Let me write it down. And then you want to apply distributivity. You get a plus a times a plus 1. Never mind, right? We're running some cyclicity. Right? You're trying to prove a plus a equals like something, just a single variable, and now you get something like this. Right? And it's hard to, you're not making much progress. A plus 1, you can claim this to be a 1, but that is a theorem. It's not an axiom. And you cannot use it yet, right? And until you prove it. Use the second one.
Yeah.
So we restart?
Yeah.
Okay, let's restart. A times 1 plus a times 1. We are applying identity twice. This is equal to a times 1 plus 1. So we're using distributivity by going from the right-hand side to the left-hand side, which is perfectly good. Yeah, keep going. Who tells you 1 plus 1 equals 1? That is true. That is, of course, correct, right? It's a true statement. 1 plus 1 equals 1 in this two-value Boolean algebra. But that's not any of our axioms. The identity? But the identity is saying that it's like it has to be 0 or something. This just shows you how difficult it is to even prove these very simple theorems in a very limited space. Right? If you have to use the axioms, you really have to think about the very, very fundamentals of Boolean algebra, which quite a bit limits your ability. Any other ideas? Right? How you wanna? You can just try it out, and we can try it out together, and see if we can probably find a good sequence of steps. Again, here we are dealing with constraints, right? Proving theorems based on axioms. Even though the theorem looks very simple, it can be quite complicated to prove. Yeah, anyone want to just try out a different set of Boolean axioms? No? All right, I'll show you one, and then probably this is the first example. So then later on, you can also get comfortable with using Boolean axioms. So I would say a plus a is the same as a plus a times 1 by identity. All right. And then if I apply distributivity, I get a. Oh, sorry. So, okay, I want to show you an incorrect sequence, a sequence that is not helping me. Right? That would be I apply distributivity. Right? I can apply distributivity, but what I end up getting is like a plus a. So I'm not making any progress. Right? So for that reason, I probably want to try something different at the second step. Well, 1, based on this complement axiom, right, would be a plus a times a plus a prime. Right? And now if I apply distributivity, well, I'm going to factor out this common variable, right, a, according to distributivity from right to left. And that will give me a plus a dot a prime. A plus a dot a prime based on complement is a 0. And this one based on identity is a. Again, I'll just write out the Boolean, the axioms I used at each step. Firstly, I use complement. Secondly, I use distributivity. Thirdly, I used complement. And finally, I used identity. With this sequence of primitive axioms, I'm able to prove that seemingly trivial theorem. And this will remain true for any number of variables. Right? I didn't use any specific property with 0 and 1. Everything I used are some axioms. So I'm going to move it a little bit out of my way so that I can write the other proof. Right. So the other proof, right, A dot A equals A, you can just really follow pretty much the same procedure, but pretty much shuffle the AND and OR, and then switch 0 and 1. So you could say, well, A dot A is the same as A dot A plus 0, which is the same as A dot A plus A dot A prime, which is A times A plus A prime by distributivity. And A plus A prime is a 1 by complement, which gives you an A. And this sequence of proof, if you write out the axioms you use, will be the same as the other proof. Right? But you're just using the other side of the proof. Right? For each axiom, we have like 2 definitions. I'm just using the opposite one, and then you're able to make the proof. All right. So then now we have proved idempotency. Right. If you want, you can use it for your subsequent proofs. So let's try another one, identity absorption. Right. A plus 1 equals 1. Again, which is very easy to prove using the truth table for 2-valued Boolean algebra. But our goal is to algebraically prove it so that it will remain true for any number of elements in a larger Boolean algebra. So any ideas? A plus 1 equals 1. You know, we can just try out something together. It doesn't have to be correct. And oftentimes it's not quite right because, again, we are working in this constrained space. So we have to try many things to get it right. Anyone want to give it a try? You want to try it out? Maybe we can use the complement. OK. Yeah. Let's see if we use complement. So this is A plus. You want to replace 1 with A plus A prime? Yeah, maybe. A plus A prime. And I think this is probably what you want to do. You want to regroup these variables, A plus A prime. Right? A plus A, based on what we just proved, idempotency is just A.
Yeah, I didn't know if we could use.
We'll get back to that in 1 second, right? And then this gives you a 1, which is a very elegant proof, except that at this step, you're actually using associativity. Associativity. Right? You're regrouping these variables, and that is associativity, which is something we have now proved, so we cannot use it yet. All right, very nice try, but except that at 1 step we really need another theorem. So yeah, we need to try something else. Anyone else want to give it a try? Okay, if not, I'll show you this proof as well. So A plus 1. Okay, I'll do this is equal to A plus 1 dot 1, right, by identity, which is the same as A plus 1. 1 can be replaced with A plus A prime by complements. And then I can apply distributivity to factor out the A variable, A plus 1 plus 1 dot A prime. Right, this is by distributivity. One dot A prime by identity is just 1 plus, that's A plus A prime by identity. And finally, A plus A prime by complement gives you a 1 Again, this sequence of primitive proofs allows you to prove the theorems based on the axiom. So on the right-hand side, we essentially apply the same sequence of axioms, but use the other one, right? Every axiom has two different equations. We use the other equation. So A dot 0 will be A dot 0. Well, I'll follow the same methodology by first expanding it with a constant, and then replacing the constant with product based on complements, and then apply distributivity, right? And then apply identity, and apply complement. Right? I don't even have to rewrite the axioms I use because they are exactly the same. Right? But instead of using, let's say, this one, now I'm using this one. All right. Any questions so far? Right, and like I don't expect you to be able to find out this sequence, right? So that's like a big relief. You just have to be able to follow it, right? To appreciate the fact that we can indeed prove these theorems based on axioms. Yeah. So really don't worry about like finding the sequence, but if I tell you the sequence of axioms that you should use, you better be able to write out the proof. Right? That is like my expectation for this part of the class. Absorption. I don't want to give this a try. Absorption. Again, you already proved idempotency at identity absorption, right? So A plus A equals A dot A equals A, and A plus 1 equals 1, A dot 0 equals 0. So you can use them in your proof. Right, so our job is getting easier and easier with these additional theorems. Yes, Max.
I just saw it. Oh, yeah. So you
don't worry. Yeah, just give it a try.
I think you're going to take the A out, right? So it'll be A times 1 plus B?
Yeah. So formally speaking, we first apply identity. A dot 1 plus AB. Right? And then we can factor out A. A dot 1 plus B.
Plus B?
Mm-hmm. 1 plus B?
Can you say that's 1?
Yes, that's identity absorption. 1 plus any variable gives you a 1. So you get A dot 1, which is A by identity.
Yeah.
That's a perfect proof, right? By reusing what we have just proved, right, like identity absorption, our life is getting easier. It's getting easier and easier, and it will only get easier with more theorems that we see in this class. Very nice proof. So again, let me write out the axioms that we used at every step. So this is identity. Next step, this is distributivity. Next one is identity, absorption. And then finally, identity. So the other one, right, you must be able to prove it using the same sequence of axioms. So A dot A plus B can be written as A plus 1 dot A plus B, which is A plus 1 dot B, which is A plus 1 dot B, which is, sorry. A dot A plus B. Oh, it should be at 0, sorry. Right. Okay. So apply distributivity, 0 plus 0 dot B, which gives you A plus 0, which gives you A. Again, with the same sequence of axioms, right? By using the other axiom, you can make that proof as well. And finally, associativity. Right? This is something that is very hard. Right? For one thing, we are having one additional variable, and also we're dealing with these parentheses. And you have to somehow eventually map it to distributivity, because that's the only axiom with parentheses. I'm not going to show the full proof, but I will show you essentially how to get started. So for the first proof, I'll treat the left-hand side as a single component. I'll call that x. The right-hand side as a y. Right, so I'll just write it down formally. So x equals a plus b plus c. Y equals a plus b plus c. This is only for my convenience because I'm going to refer to them again and again later. So I better just create a single variable to represent that expression. And then what you can prove is that step number 1 would be you can prove that ax equals a. Right? Any of those variables, the variable that is part of x, when you multiply it by x, you get back to that variable. Right? And the formally speaking, this would be aa plus a b plus c, which is the same as a plus a b plus c, which is a. So you just prove that ax equals a. And step number 2 would be we're going to prove that x dot y equals x and x dot y equals y based on the result from step 1. Right. Again, don't worry about this particular proof. It's a more complicated proof. And this is only just for your curiosity and for reference, right, for completeness. Right, but feel free to try it out by yourself. And when you do a search, right, just search on Google how to prove the associativity of Boolean algebra using axioms, and then you'll find the complete proof. All right, so what we have just seen are several X theorems, right? Idempotency, absorption, identity absorption, associativity, proven based on the axioms. Involution, you can use this that as an exercise. It's not too complicated to prove. All right, so now in our arsenal, we have a lot more theorems. And the next theorem we're going to see is called De Morgan's theorem. And of course, it's named after a guy, Augustus De Morgan. De Morgan actually wrote something about Boolean algebra a little bit earlier than Boole. He wrote a book, The Mathematical Analysis, on the structure of syllogism in 1846, 1 year before Boole's work on his algebra. Right, 1 year before Boole's The Mathematical Analysis of Logic, which eventually becomes Boolean algebra. And he was a good friend with Boole. They knew each other since around 1942. And at that point, again, they were running into a fight with Sir William Hamilton, who was the advocate for predicate logic. And they're just trying to support each other. Like De Morgan and Boole, they're trying to support each other in this fight. And Boole was actually motivated by De Morgan's work in 1946 to develop or complete his algebra, which eventually becomes Boolean algebra. And they're still friends after 1946, 47. They have been friends for their whole life. And then they were supporting each other's works, doing proofreading for each other, advocating for that Boolean algebra, again, as a general reasoning tool, right? Like modeling any problem as an equation in Boolean algebra. So that's a history. And now, from today's point of view, the only thing we care about is De Morgan's law. It's good that there's still a law named after De Morgan because he did make a lot of contribution to Boolean algebra. De Morgan law is saying that x or y, you complement that full stuff. It is the same as you complement each individual variable and then switch the operation. And then I would say a good tool to visualize this behavior is through Venn diagram. Right? Probably have seen this diagram in abstract algebra, like studying set and graphs and intersection, that kind of stuff, right? Union. So let's try to map this into the Venn diagram. So x plus y complement, right? X plus y is this region, right? This whole thing covered by either x or y. That's x plus y. So the complement would be this outside region. Right. So this is x plus y complement. I'll write it to the other side, x plus y complement. So, and that is my left-hand side. The right-hand side is saying x prime intersect y prime. So I will draw one Venn diagram for x prime, another one for y prime, and finally x prime dot y prime. So x prime is anything but x. Right? So that is x prime. Can you see the color all right? Yeah. And then y prime would be anything but y, so this outside region. Right. That's y prime. And their intersection, right? And get essentially checking for intersection. And their intersection is exactly this outside region, right? When it's not covered by x and not covered by y. Right? From these two, you take the intersection, you get x prime dot y prime. A pretty cute visualization. You can prove this from Boolean axioms, of course. That's by the definition of theorems. Right? But I would say once we've gone past that initial exercise, then we better find some visual tool. And we're going to see a lot of visual tools to help you simplify the proof steps further and further. Right. So I just made this proof. Right? One side of De Morgan can be proven using Venn diagram. The other side, you can also prove it using Venn diagram, even though that's a little bit more like harder to visualize since we're drawing like a big region of x prime and y prime and take the union. Right? But still all right. You just expand that a little bit further, you can make the other proof. Even more Boolean theorems. We're almost reaching all the Boolean theorems. They're about, I would say, 9, 10, 11, roughly, Boolean theorems. And we have seen most of it. The other important one is consensus. Consensus is saying that xy plus x prime z plus yz, you can essentially get rid of this yz, right, without changing the expression. And then the way I look at it is really the other two terms, one of them has an x, the other them has an x prime. So you pick the remaining variables or sub-expressions and then combine them into a single term, and this term is redundant. There's no need in keeping this additionally combined term, one variable from the x side, the other variable from the x prime side. So you can prove this using Boolean axioms and theorems pretty easily, right? So I can say, well, xy plus x prime z plus yz is the same as, well, yz, you can multiply this by x plus x prime. Right? And that allows you, when you apply distributivity, to create two additional terms, xy plus x prime z plus xyz plus x prime yz. And now, if you look at this xy, compare it with over here, you can apply identity absorption. Identity absorption saying that a plus ab equals a. Right? So a is a variable or sub-expression appearing in both terms. And xy appear in both of those two terms. So this one can be eliminated. And also, x prime z appears in both terms, which only keep, you can call that you only keep the bigger ones, or you only keep the ones with fewer literals, right? They really mean the same. You can get rid of that, right? And now you can make the proof using Boolean algebra. You can also look at it in terms of the Venn diagram. Again, I'm going to show it over here at the bottom. I will show xy plus x prime z plus yz on one side, xy plus x prime z on the other side. So xy is their intersection. X prime plus z is within z but not within x. So this part of the diagram. And that's your overall expression on the right-hand side. On the left, you still have these two sections, x prime z and xy. But you have one thing That is actual. And that is this part, the intersection between yz. Right? But you see this intersection has already been covered in part by xy, and for the other part by x prime z. So there's no need to additionally include that intersection. Right? It's like, again, it's a redundant part, has already been covered fully by the other two terms. And similarly, you can also use the Venn diagram to prove the other consensus. Again, by flipping 0 and 1 and flipping the operation, you get yet another equation. Right? You have one valid equation, you flip many of the things, you get another valid equation. And this idea, formally speaking, is called the principle of duality. Right? The reason why we have two equations for each axiom and for each theorem, except for duality, of course, except for the involution, because involution involves only a single variable, is because of the principle of duality. Given one valid Boolean expression, and you need to prove it. You need to prove that equation to be valid. You can swap and or, swap the operation, and then complement zeros and ones, right? Switching between 0 and 1 to get yet another valid Boolean equation. So here we're talking about the relationship between two equations. One of them is, in this example, right? One of them is consensus number 1, right? The first theorem in consensus, the other one is consensus number 2. And once you make one of the proofs, you don't have to prove the other. The other one will be true because of this principle. Any questions so far, right? What we have just seen, we saw the Boolean axioms at the beginning of this lecture. And then we went through a few proofs of the fundamental theorems. And then we proved a few more complicated theorems, like the Morgan consensus with some visual aids. And now we're deriving this principle of duality, saying that any proof, once you prove it once, right, with one composition of and or, you can flip that operation and flip zeros and ones to make the other proof. You don't have to worry about doing two proofs. And it's for that reason why these proofs, right, for equation number 1, equation number 2, they can be proved in the same step because of this duality property of Boolean algebra. All right, yeah, any questions? So this is a more complicated proof. I want to show you as an example. You have left-hand side, right-hand side. They just don't have anything in common. Right? These are completely different looking expressions. I don't see anything in common, right? But they are equal. And the question is, how could you approach the proof? Well, in this scenario, I would like to use consensus, because consensus allows me to introduce one additional term that looks kind of similar to the other one by picking only a part of the expression from each sub-expression and then build new terms. So from these two, for example, from these two terms, when I apply consensus, I can add b prime c to my expression to the left-hand side without changing the meaning of that expression. Right? If I pick a plus b and bc, and again, now I'm looking at the anchoring point of the b variable, right, appearing as non-complemented in one term and complemented in another. So I can add in a prime c prime to my left-hand side. And then finally, between ac and c prime, again, I first look for this anchor point, which is the variable c. So I'm going to combine the other two terms, a from ac and b from bc prime, create a new product, and then add it into my expression. All right. So what I've just did is I'm really saying that the left-hand side is the same as the left-hand side plus the right-hand side. Right? Like these three new terms, they all belong to the right-hand side. And I just have to apply this proof one more time to get rid of the left-hand side so that I can make this proof happen. From these two products, right, again, the anchor point will be c, because I have c and c prime in the two terms respectively. So a prime b, that is a redundant term. Right? I'm applying the Morgan in the opposite direction to get rid of some of the terms. Just show that in a different color. Right, these two get rid of A prime B prime. And B prime C and AB, again, anchor point will be the B variable. So A and C combined, that is a redundant term. And finally, A prime C prime and AB, you have A and A prime. So you combine the other two terms, B and C prime, and that is a redundant term. And now you have completed the proof. I didn't write it down entirely, but you see the point. Left-hand side can be expanded and then reduced to get rid of whatever appears in the original left-hand side so that you arrive at the right-hand side. Yeah, any questions?
Can you explain that again?
Which part? Yeah, so I'm saying that, well, if I start with my left-hand side, A prime B prime plus AC plus BC prime, I can first add additional terms by applying consensus, which allows me to add BC plus A prime C prime plus AB. Right? So consensus can be used to add additional terms. And now I have a longer expression. I want to reduce it down to the right-hand side by applying consensus the opposite way, from a larger expression to a smaller one, by getting rid of some of the consensus terms. But I will not get rid of the terms that I just added. Those are my right-hand side. I want to keep them, but use the right-hand side to get rid of the left-hand side. Right, so now I assume this part should be the equation I don't want to touch. I want to see which are some consensus terms that can be generated based on those three terms. And A prime B prime would be the consensus between these two. Right. AC is the consensus between these two. BC is the consensus between, BC prime is the consensus between those two terms. So now I can also reduce down the size of my expression until it reaches the right-hand side. Again, left-hand side equals left-hand side plus right-hand side with all 6 terms. And then you can use the 3 right-hand side terms to get rid of the 3 left-hand side terms. All right, so here's a summary of many of these more advanced Boolean theorems. We saw De Morgan, a good friend of Boole, and then they were supporting each other. Consensus is a way to add additional terms and also eliminate additional terms, right, to get rid of all the redundancy in your expression. And uniting, well, these are like simple simplification theorems derived based on the other theorems and axioms. Xy plus xy prime, you can just factor out x, y plus y prime, which gives you x dot 1, which equals x. Right? A very simple theorem based on the other theorems, but you don't have to even remember this. You can just apply it on the fly using the basic theorems. Elimination, saying that, okay, I can apply distributivity, x plus x prime, x plus y equals 1 dot x plus y equals x plus y. Right, a way to get rid of one of these literal when you have a larger term that appears in the non-complemented form. Distributed consensus, this is nothing more than applying distributivity and then followed by consensus. So again, these are some of the things you don't have to really memorize. And you really don't have to memorize any of these because there's a handout on Canvas showing you all the axioms and theorems, and then that will be provided at the end of the midterm and final. So you don't have to even keep that on your notes. And as I told you earlier that Boolean algebra, we could have a 2-value Boolean algebra, the one that we use for switching circuits. We could also have a larger Boolean algebra, and there are many classes of Boolean algebra that we use in many other classes, linear algebra, in abstract algebra classes. You have actually already seen some other Boolean algebras. And those other Boolean algebras, they tend to have more elements. But still remember, we proved these theorems algebraically based on the axioms. So you can also apply the very same theorems to a larger Boolean algebra with more elements. One of them I want to point out is this algebra of classes. Right? You can think of 0 and 1 as an empty set and a set with like a single element. Right? And then you use union and the intersection to replace or and and. And again, all of these algebraic rules will remain valid. And let's try to, again, think about this formality about Boolean algebra and develop a four-valued Boolean algebra. And I would define the same. I'll just define two arbitrary operations as AND operation and OR operation, but these are really have nothing to do with the original AND and OR operation. These are just arbitrary functional designations. And again, following these axioms and theorems, I'm able to fill in the truth table for these larger functions to build a Boolean algebra. Right? Boolean algebra is an algebraic system. And as long as it satisfies these axioms, that is a valid Boolean algebra. A, B, C, D. Right? These are just, again, some arbitrary symbols. Right? Don't have any meaning. And I would just claim D to be the identity element for one of the operators, A to be the identity element for the other operator. What I can do is I can follow some of these axioms to fill out the table. Right? For example, identity. Well, I will just copy over the headers A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. Because no matter which variable I use to operate with A through this gate, through the identity element for OR function, then I'll just get back the same input variable. Right? So even for these abstract definitions, I can fill out those columns and rows. And then that's how I use identity to fill out parts of the table. Right? Idempotency is saying that an operator, a variable, operating with the same variable gives you back this variable. And that will show up as a diagonal of A, B, C, D. Right? A, B, C, D. C or C is C, D or D is D, B or B is B. And you get to fill out more of the table. Commutativity, I'm already using commutativity, right, to keep this table symmetric across the diagonal. I always have that in mind. Identity absorption. So A or the identity element of the other function will give you back the identity element. So abstractly speaking, I get to fill out those as D's. Right, D is the identity element for the AND operation. And based on identity absorption, I'm just replacing 1 with D. And now the table will have a row of D when the input variable, one of them, is the identity element of the other operation. Right. Similarly, I can replace 0 with A. And then that gives me this row and column of A's. And A and D are complement to each other. You can verify that they satisfy the complement axioms. So this is D, this is A. Right, A and D are complement to each other. B and C are also complement to each other. In any Boolean algebra, every element needs to have a complement, and its complement has to be unique. So if B and C are complement to each other, right, B and C should give you the identity element of the other operations, right, which is A. And B or C, again, should give you the identity element of the other operation, which is D. All right, that's how you build a four-valued Boolean algebra using these abstract symbols. Right? What's the meaning of this Boolean algebra? We don't quite know. But a slight hint I can give you is that you could think of this as, A equals empty set, B equals a set with a single element, 1, C is a set with a single element of 2, D is a set with 2 elements, 1 and 2. Right? The power set of the set 1, 2. And then OR is the same as union, and is the same as intersection. Will probably give you a more intuitive way of appreciating the four-valued Boolean algebra. Right? So OR is a way for you to grow, and is a way for you to go down. Right? That's in essence what we're doing over here. So I want to show you a few more things. Boolean expressions, you can have that complicated multi-level form, have through that hierarchical decomposition, or there are some more common representations, common forms of Boolean expressions. One of them is called sum of products. Sum of products is an expression with a bunch of products. Product is essentially and of some variables. A bunch of products. Those are ORed together. Right? Sum is essentially an OR function. Product essentially an AND function. This is just how casually and commonly people call AND and OR gates. Right? Sum of products is a sum of a bunch of products. And each product is a product of variables. Product sum is a product of a bunch of sum terms, a bunch of OR terms. Right? These can also be called OR of AND or AND of OR expressions. And as it turns out, you can represent any Boolean expression using in this form. You can convert any Boolean expression into either of the two forms. Right? So why do we care about these two forms in particular? We're going to see a lot of logic minimization algorithms in these two forms. Because it is a very simple representation, you can define some optimization principles and optimization algorithms more easily compared to an arbitrary composition of AND and ORs. Right? And also, if you draw this as a circuit, your circuit will look like an OR gate at the output with a bunch of AND gates at the inputs. So you have all the inputs on one side, the output on the other side. And the information will just flow from your inputs to outputs. And that information flow only goes through two gates in comparison to, let's say, in this example we saw at the beginning, goes through 3 levels or 4 levels of gates. So it's also the fastest implementation. Right? 2 levels is the best you can do to be able to still implement any functions by getting the maximum performance. And for those reasons, we care about 2-level logic minimization. And between these two representations, sum of products and product sum, you can do conversion between them. You can actually convert any expression into either of the two by applying a bunch of distributivity. Right? Starting with the sum of products, what you can do is you can consider the first 2 terms as a sub-expression and then apply distributivity within those 2 terms. And that will give you essentially all the combinations of individual variables, A or C, A or D prime, B prime or C, B prime or D prime. That translates into 4 sum terms. You can do this one more step by treating A and C prime as 2 separate variables and then apply distributivity. Right? Add A to each of those terms and then add C prime to each of those terms to get a product of sum. Right? Now if you look at this final expression, we have 8 parentheses. Within each parenthesis, we have an OR function. That's a sum function. And at the top level, they are collected together through an AND gate, right? Or as a product function. So that is a product of sum expression. And if you want, you can do some further simplification by applying things like consensus and uniting. But again, let's not worry about that for now, right? That's more for the optimization part of the class, which we'll see in the coming, I would say, 3 to 4 lectures, right? How to optimize a combinational circuit to get the minimum SOP or POS expression. And this is one example from your today's workbook. And I'm essentially giving you the solution in lecture. Again, this is a product of sum, right? A product of 3 sum terms, or of 3 AND functions. We want you to convert this into a sum of products. You can apply distributivity, of course, but that's usually not the most optimal simplification step. Distributivity generates a lot of work. You can do better. You can do better by observing if there's anything that is shared in common between some of the terms. What I see is that A prime C prime is shared in common between the first 2 terms. So what I can do is I can factor out that one first. Again, I'm applying distributivity, but rather than distributing each individual variable, I can distribute on a sub-expression of A prime plus C prime, right, plus BD. And then B prime plus D prime. Right? I'm actually only one step away from nearly the final expression. And the observation I'm making is that BD is the complement of B prime plus D prime. That is by De Morgan. Right? De Morgan is saying xy prime equals x prime plus y prime. Right? You replace x with b, y with d. You're really observing the complement of two expressions. And how do we use this complement? Well, we have this a plus a prime b, which gives you a plus b. Right? You can get rid of one of the terms. In this case, you can get rid of the BD entirely. We are still applying Boolean axioms and theorems, but we can apply them on a larger group of variables on an expression basis, right? On the basis of some expressions. So I get a plus c prime times b prime plus d prime. Now you just apply distributivity to get a sum of products, right? Just one step away. It avoids a lot of the work that would be generated if you apply the brute force distributivity method. Right. And one last topic I want to talk with you today is a thing called universal gate. Right. This solves another fundamental problem, which is, what is the minimum set of gates that can be used to build any logic? We need to answer that question to prove the feasibility of any new technology. Right, let's say, actually, a universal gate is something that can be used to build any logic functions. In other words, they can be used to build AND gate, OR gate, and NOT gate. The reason is because we can represent any Boolean expression in that two-level SOP or POS form. Therefore, if we can build an OR gate, AND gate, and inverter, we can build any logic function. And or not together, they are, of course, a universal gate. That's the definition of universal gate, actually, right? So that you can build any SOP or POS. There are some other examples. NAND gate by itself is a universal gate because you can use it to build AND, OR, and the inverter. And this kind of proof is what you need to do to prove that something is a universal gate or universal set. To build other gates and or not with the new gate. So for example, this is a NAND gate, an AND gate with a bubble or inverter at the end. If I want to use this to build an inverter, I can connect my variable to both sides of the NAND gate, and then what I will get out is an X complement. So I'm using the NAND gate as an inverter, right? That's building the inverter with the NAND gate. And since I already know how to build an inverter, I simply need to add that NAND-based inverter to the output of a NAND gate to build an AND gate. Right? X NAND Y getting complemented, just X and Y. Right? Double inversion cancels out. And this inverter will be built based on that NAND gate as well. Right? A purely NAND-based AND gate by using two NAND gates. And finally, I can build an OR gate by, how do I do to get an OR gate? Any ideas? Using the NAND gate, how to build an OR gate using NAND gate. All right, so I'll show you this one. If you can double complement the inputs, you get an OR gate. And this is by De Morgan. X prime and Y prime complement is X plus Y. Right? A lot of inversions at the input and output of NAND gate allows you to get an OR gate. NAND gate, that is your base gate. Adding actual inverters to the inputs are no other than adding some additional NAND gate. Right? So now you get to get an OR gate, X plus Y. All right. So I think that's the end of today's lecture. I'm going to continue on what we're talking about today, finish this discussion on universal gate and show you a little bit about XOR and XNOR and how to manipulate Boolean expressions with those additional operators. And then after that, we're going to move on to some more powerful representations, which is called a Carnot map. And there might be like one or two questions in today's workbook that you cannot quite do yet. I think there's only one question. But just do the rest, and then you still have until Wednesday to submit it.
We're able to.
Yes.